By the way, the Doppler shift also applies to light. We'll get to that next semester. But the math is different. Part of what I did so far was assuming that you have watched the videos. If you have not watched the videos, then please do so. Suppose I have a box. And I am going to grab something from my office. Pause this. I have a box here. I'll add some dimension to it. With gas inside. Each of these particles is moving around at some speed. And I want to know, come up with some way of estimating the impulse exerted on the box. So I'm just going to look at that one wall for right now. So in time t, what is the impulse exerted on the right side? All right, so let's take a look at just a single particle for right now. So if I have a single particle coming in, it's going to hit the wall and it's going to bounce off. We're assuming perfectly elastic collision, because, well, at that level, it probably is. We assume that the wall is, for the most part, not moving. This has some initial velocity, and then a final velocity. Particle, whatever particle this is, it has some mass m. So first off, what is impulse?
The change in momentum?
Yes.
That's cool.
What letter did I use for impulse? Did I use I or J?
You use J. We use I, but he uses J. Okay. But can you use I?
Yeah, as long as there's a vector symbol over it. Usually from context, you can pick out what it's going to be. I'm going to use J for this. I can't remember what I did before, so if I used I vector, fine. I'm using J vector now. I probably should standardize it into one thing. So the J on the wall is going to be equal to the negative of the impulse on the particle. I'll just put it in there. It's a closed system, so whatever one gains in momentum, the other one's got to lose, so they're going to be opposites of each other. So that would be equal to the change in momentum, the negative change in momentum of the particle, which is the negative final momentum of the particle minus the initial momentum of the particle. Distributing the minus sign, we end up with Pi, the initial momentum of the particle minus the final momentum of the particle. Let's set up a coordinate system here. Oh, side note while I'm thinking about it, at this point, we've done everything in the Rube Goldberg test. I believe I have not only posted a written out solution, I think I have videos of the solution as well. So at least they've written out step by step. And I'm not pushing that because it's the test, the final test, but I'm pushing it because it covers all the stuff that we've done for the last test. So, if I break this down into its components, and you know what, we can go for the typical stunning visual effects. This would be VI, called VIY and VIX. So my initial momentum is M VIX I hat minus M VIY J hat minus my final momentum, which will be negative M VIX I hat minus M VIY J hat. Take a moment to convince yourselves that there's not a mistake there, or if there's a mistake, to point it out. And so going through the fancy math there, we end up with 2 times the mass of that particle times VIX I hat. That is the impulse on the wall. I know that also has to be equal to the average force times time. The other definition of impulse is not only change in momentum, but force times time. So that's going to be equal to the average force times time. Now typically I put delta t, but I've already defined that we're talking about a time of t. Well, actually that's somewhat misleading there. That would be the force of a single particle, but I've got more than one particle hitting the wall. If I just have a single particle hitting the wall, that is going to be so tiny that it's negligible. But I've got a bunch of them hitting the wall, so I have to figure out how many of these particles are actually hitting the wall. So I'm just going to say that NCOLL are the number of particles hitting the wall. Hitting the right side. So really the average force that I care about times time is equal to the number of particles that collide times 2mvix. Well, that means that the average force then, well, just divide by time. Two integral over time in VIX. All right, so we should be able to do better with number of particles that are going to collide. Because if I have a certain amount of time t, I mean, some of the particles won't have time. If the time is small, this particle doesn't even have time to get over there. So I have to, so if I go ahead and define, let's set n equal total number of particles in the box, total number of particles in the box. Then the number that will actually collide is going to be a fraction of that. So if this distance right here is that Vix times time, whatever particles are in here are the particles that are actually going to hit the right side. So if t is small, this is a very small range. If t is large, then it's a much larger range. But within a time t, only particles are going to travel whatever their Vix is that way. So we've broken this down into 2 times this fraction of particles. If I assume that the particles are evenly distributed, so if this here is length L, then it would be the fraction of Vxt over L. So this is Vxt over L. That's the fraction within that region on the right, times the number of particles over time is equal to m, not times. Times the mass of that particle times Vix. Time cancels out, that's convenient. So I'm left with 2 Vix. Over LT.
Well, we just canceled out the t's.
You are correct. So
Can we do v sub ix squared?
yes, and that's the next step. So that's going to be equal to 2 Vix squared n over L m I hat.
Is there any more we can simplify?
Not yet. We need to do another thing here. Pressure. Most of you have had some chemistry.
MMHG?
Say it again.
MMHG?
MMHG.
Millimeters of mercury?
I'm not looking for units. I'm looking for what is pressure.
The amount of force exerted on something by another something. Typically. I might be wrong.
How much stuff is in an area?
That would just be number of particles or potentially mass. All right, so
The amount of stuff that's above it that's pressing down on it?
right now I'm standing on the floor, both feet. I'm exerting the pressure on the floor. If you think of pressure as something that you would feel, if I were standing on you, you would feel it. If I went onto 1 foot, am I exerting more pressure, same pressure, less pressure?
More pressure per square inch, but the same amount of pressure totally, I guess?
No. That gets into flashing back again. My daughter was writing a formal lab report for chemistry when she was here. And she defined pressure to be a force. And I said, no, that's not right. And she said, it's what the book says. I said, no, there's no way the book says that pressure is force. She pulled out the book, went to the glossary, and it said pressure is a force. No. Then I went to Dr. Wilford and I said, the definition of pressure in the book is wrong. She said, yeah, that book's got a lot of issues. I don't think they're using that book anymore. I hope not. It's especially since my daughter took chemistry 10 years ago. Man, she's old. Anyway, it is related to force, it is not the force itself. So back to 2 feet versus 1 foot. Do I exert more pressure standing on 1 foot or more pressure standing on 2 feet, or is it the same? Okay. The force is the same. But what's different is the amount of area I spread it over.
So was I right? I feel like that's kind of what I said.
Not the last wording that you used. It is the force per unit area. The force is the same, the pressure is not. What I heard you say was that the pressure was the same.
Oh, my bad.
So I have this force acting on the right-hand side there. I'm just going to drop the vector notation here. It's just sort of a nuisance. This is the force against the side, the average force against the side. If I divide by the area, then I have 2VIX squared N M over LA. And what is L times A?
1 times area is volume.
Yes. Area, that area there is the area of this right side. So if I take that area times this length right here, I have the volume of my cube, or my box. So this is just 2VIX squared N M over volume. And I put the serifs on the V for volume to differentiate it from my V for speed.
Can I ask a question?
Yep.
So at the end of the pink on the whiteboard, at the bottom,
Okay.
right? So if the number of particles at the time of the collision times 2mvix I hat
Yes.
is the n in this case 0, because in the next thing it says that the same thing is true without the n collision.
Okay. In terms of progression, I went from here to here. This was looking at just a single particle right here. And then I said, well, we actually have more than one particle hitting that wall. And so I expanded it. So this is for one particle. This is for however many particles are actually hitting it.
Okay, thank you.
Into this. All right. Now these particles are moving in random directions. It is just as likely to be moving to the right side as to the top, to the bottom, to the left, to the right. They actually are all traveling with some velocity v on average. I know that v, the actual velocity, is going to be Vx I hat plus Vy j hat plus Vz k hat. If I just square both sides, I do a dot product with itself, I end up with speed squared is equal to Vx squared plus Vy squared plus Vz squared. Now, there's no reason to think that there's any preferred orientation here. That is just as likely to be moving to the right as up, down, left, right, back, forth, etc. So on average, my average of my square is just going to be 3 times any one of these squared. In other words, Vx squared is just a third of the speed squared. So this now becomes 2 times 1/3 v squared in over v.
Can you put parentheses around the 1/3?
Yep. Which is just 2v squared in over 3v.
Can I ask another question?
Yep.
So, underneath the 2 and colon on the blackboard, at the top. Yeah, so under that, how did you get the parentheses area?
So imagine I've got this random mixture of particles in the box.
Mm-hmm.
I know only a certain fraction of them are actually gonna hit the right side.
Yes.
And so within a time t, it's any particle with I hat direction component that is within this range. Because if it's for some time t, it's only that's how far it's gonna travel. So
Okay.
within a time t, that's the amount that can actually hit the right side. And so the fraction would be that divided by L times the total number of
Okay.
particles.
Thank you.
We are near the end. If I multiply both sides by the volume, and I do need a new page, let's see, I get 2/3 v squared. I get PV equals 2/3 v squared in L. Well, actually, as a matter of fact, I get 2/3 in times oh, we'll do that next part. No. 2/3 v squared. All I've done is just shift around the order. PV, what does that equal?